section 233, which is titled Applying Similarity. And so the first thing we're going to do is we're going to answer the question, what can I do with similar triangles? So question 100 has to do with George Washington's nose. Okay, so on her way to visit Horace Mann University, Casey stopped by Mount Rushmore in South Dakota. The park ranger gave a talk that described the history of the monument and provided some interesting facts. Casey could not believe that the carving of George Washington's face is 60 feet tall from his chin to the top of his head. However, when a tourist asked what the length of Washington's nose was, the ranger was stumped. Casey came to her rescue by measuring and then calculating to get an answer. How did Casey get her answer and then figure out the length of George Washington's nose on the monument? Work with your team to come up with a strategy. Show all measurements and calculations on your paper with clear labels so anyone could understand your work. Okay? So the first thing they want to know is, what is the actual question that they're asking? They want the length of George Washington's nose. The one on the actual monument. Now, you can't climb up there, right? They have it roped off because they don't want it destroyed. And it's huge. You would have to have measuring devices, measuring tape. You'd have to have special climbing gear, all kinds of stuff, okay? So how can we use similarity to solve this problem, okay? So if we know the length of his head, which the ranger told them was how many feet? 60 feet tall. So we can take that measurement to the length of his nose, which we don't know, so that would be x, and we could base it on something that's similar but not exact, right? Like your own head. You could measure from your forehead to your chin and then measure the length of your nose, like from the skin down here to the tip of your nose. Set up a proportion, do the cross product, and solve, okay? What are your other options, okay? Another option might be if you have one of these, right? Who's that guy? So we could use a little tiny centimeters ruler. So this is inches, right? Thank you. This is centimeters, or this is inches, and this is centimeters. So we could measure from his forehead to his chin, but we would have to use not just the centimeters, because those are bigger. We would have to use the little tiny dashes, because look at how short or how small his nose would be, right? So it's not very practical. Just so happens that he's also on the quarter here, and he's sideways in it, so it might make it, so you could measure it, but even this little tiny ruler, you would need something much, much smaller, maybe even like a small glass. So those could help you, but it's not necessarily going to get you super accurate unless you have a teeny tiny measuring device, okay? So what parts do we need to compare? You would compare head to nose. Do we need math tools? Yes, we need some way to measure, some sort of ruler or some sort of measuring tape, something that would help us, okay? All right. Question 101 says, are you getting sleepy? Legend has it that if you stare into a person's eyes in a special way, you can hypnotize them into squawking like a chicken. Here's how it works. You're going to place a mirror on the floor. Your subject has to stand exactly 20 centimeters away from the mirror and stare into it. The only tricky part is that you need to figure out where You have to stand so that when you stare into the mirror, you are also staring into your subject's eyes. If your calculations are correct and you stand at the exact distance, your subject will squawk like a chicken. Okay? So I have measured the tiles on the floor in our classroom, and they're each approximately 30 centimeters. So to get to as close to 200 centimeters as possible, we're going to go 6.5 of the tiles. Okay, so from side to side or front to back, depending on how you're looking at it. And so you're going to send 6.5 tiles. Then you're going to put your mirror. And then the person you're doing this with is going to go 6.5 tiles the other direction. Okay? What's going to happen is you're going to have the mirror. I put a little M for the mirror in the middle. One of you is going to stand here. One of you is going to stand here. And you're creating triangles. You're going to have a right triangle over here and a right triangle over here. And then you're going to have your angles down here. You're going to try and look into each other's eyes. And when you see each other's eyes, you're supposed to squawk like a chicken. Or we'll just raise our hands, okay? Now for the moment of truth, have your teammates stand 200 centimeters away from the mirror. While you stand at your calculated distance for the mirror, are you making eye contact? If not, check your measurements and calculations and try again. Even though it did feel like it looked like you were just trying to see each other's eyeballs, you were actually forming similar triangles by what we call angle similarity. You created a triangle with you and that mirror and the person standing on the other side. Because you both have a 90 degree right there, and you both have congruent angles in the middle, so that's angle similarity. Cool. All right. Anybody still writing? All right, flip over to the top of page 26. Get all the way up to the top here. Okay, question 102 says, lessons from abroad. Latoya was trying to take a picture of her family in front of Big Ben Clock Tower in London. However, after she snapped the photo, she realized that the top of her father's head exactly blocked the top of the clock tower. While disappointed with the picture, Latoya thought she might be able to estimate the height of the tower using her math knowledge. Since Latoya took the picture while kneeling, the camera was already 2 feet above the ground. The camera was also 12 feet from her 6-foot tall father. So we put a 12 right there. The camera was 2 feet and her father is 6 foot. Okay? And he was standing about 930 feet. So the distance from her dad to the clock tower was 930 feet from the base of the tower. So for part A, it says, locate as many triangles as you can in the picture at right. Can you identify any triangles that must be similar? If so, explain how you know they are similar. Okay? So we actually have 1 triangle, 2 triangles, 3 triangles. All the 2 smaller triangles are drawn within the larger triangle. Okay? They all have what we called a shared angle at the ground way over here. That's why I put a triple arc. That triple arc is part of the small triangle, part of the middle triangle, and part of the large triangle, including Big Ben. BB is Big Ben. We want to know how tall is Big Ben based on her 6-foot father, based on the 2-foot camera off the ground. Okay? They all have 90-degree angles as well. There's a 90 here, there's a 90 here, and there's a 90 here. So you draw in those little boxes. Okay? All 3 of these triangles are similar by angle similarity. They have this shared angle down here, and then they all have 90, 90, 90. Okay? For part B, they want us to use the similar triangles to determine the height of the Big Ben clock tower. So we're going to set up a proportion using the measurements we know and the one thing we want to know. We want to know how tall is Big Ben, right? So that's where we're going to put our X. That's Big Ben's height versus how far all the way to this angle over here, which is 942. You add the 930 plus the 12, you get 942. Okay. We also know that we've got 4 to 12. Okay, so the difference between the 6-foot dad and the 2-foot camera is 4 foot, and they're 12 feet away from each other. Okay? So we're going to take our proportion where we set it up. We're going to do what's called the cross product, which means we're going to multiply diagonally. So I did 12 times x and 4 times 942. Then I took my calculator and simplified. So 12 times x is 12x. And then 4 times 942 is 3,768. We divide both sides by 12, and we get 314. Then we add back the 2. The 2 is the height of that camera. And we determined that Big Ben is 316 feet tall.